propellant ingredients. After that, he joined as a senior project advisor to Mukund Limited for designing of equipments, preparation of design reports and data documents for the second launch pad of and Sierra Quota. From 1997 to 2000, he was on his own as a managing partner with Medipack Products in the development of process and integration of sanitized sterilization products and equipments for medical and food processing industry. After that, he was a consultant come resident engineer with Tifac DST. Simultaneously was working as consultant to Tifac DST for evaluating and monitoring of funded research projects. He has also worked as a director, Asia Contact Lens Laboratory in development of ophthalmic equipments. And his entire journey of careers, he has won several awards. Few of them are as follows. He received an NRDC, that is National Research and Development Council Award for the development of indigenization of rocket propellants. Received a Most Active Research Scientist Award in the year 2008 from VIT University. Is currently a member in subcommittees of Kerala State Science and Technology and Kerala State Industrial Development Corporation, formed to study the process of feasibilities, impact analysis, and pollution control. In his entire career, he has done on various assignments like he's installed and erected a commission a 10 kilowatt solar dish sharing engine, the funding from NMRE and a know-how from SVP Germany. Which is a new research and development program which is under progress to hybridize the biomass gas to improve the capacity utilization. He has also installed a 10 kilowatt solar PV unit for supplying power to computer sensors. Erected and commissioned 100 kilowatt biomass power plant in Dubai in dual fuel engine and improved the process equipment for using locally available biomasses. Has developed carbon dioxide driven vehicle as a part of carbon dioxide research and development program. A new carbon dioxide based fuel is being developed to use carbon dioxide as working fluid in icing. This is the brief introduction or background of Dr. Natarajan, and definitely today's subject is very interesting, which it's a totally unknown subject for all of us, sir. Since sir had joined here, I'll request Natarajan sir to take it forward from here. Our director Harish Patel also will be presenting along with him in this end.
Slide now. See, this is something to do with what we have, the whole world has been grappling with. People are wanting the CO2 to be bound in some way so that it does not affect the climate. Climate change is a very disastrous thing which is happening. You must have seen very recently there was such a big heat wave that we were. I live in Pune where the temperatures have never gone beyond 35, 36, and temperatures here are 42. So this kind of heat wave, and in many countries there's been a very bad cold wave. So extreme climates have been seen because carbon dioxide is rising every year beyond the levels that were envisaged, and it is causing a massive climate change. People are trying to control that. We should not have an overall more than 2 degrees temperature rise. So if we go to the second slide, microalgae, people have been working on for years, and we also have Amrish here in the call. I think he's still there. Amrish, he can also explain to us how algae has been a major area of research. We can produce oil. As per Mr. Natarajan, it says that 5,000 to 15,000 gallons of oil can be produced per year per acre, which is far beyond the what you call the production that can be achieved from corn, soybean, or sunflower. In America, many farmers have taken up corn farming because they find it lucrative. Power gen. Go to slide 3. Theoretical limits. Maximum yields of microalgae in open ponds. So there are various types of algae, and here you can see that Vellore Institute has worked on many types of algae, and the result they have got is best with the marine. What Dr. Natarajan and others have worked is how to produce algae on solar PV panels. So not only that you are capturing photons, the photons of the sunlight in the form of microalgae, but you are also capturing these photons in the solar PV panels which are below. So what he has done is he uses wastewater. Not if you take fresh water as it is, the fresh water sources in the world are very limited, and if we start using the fresh water for growing algae, and then thereafter producing oil out of it, there will be a crisis of water availability. So what he has done is he has taken wastewater and used that for algae production. And the algae production, he does it not on a plain surface, he does it on the surface of a solar PV panel. So as per him, more than 90% of the solar energy can be captured. 70-80% of the solar energy is captured by the algae itself, which takes 8 to 10 days to grow. In 8 to 10 days, you can grow the algae, take it out on one side. The whole solar PV panel is on a small incline where you have thrown the wastewater, and there you have also thrown. We will have lots of questions to ask Dr. Natarajan.
Okay.
Let me see if I can still get him. Otherwise, whatever knowledge Amrish has, I will request Amrish to give us some.
Then we have the same thing. We had genetically engineered on a few of these microalgae to produce oil and alkanes.
Okay.
But it was in lab scale. At the most pilot scale. We didn't go to such huge scale.
Okay. This algae can be produced in hydroponic culture form, hydroponics, because see, Dr. Natarajan has talked about per acre, right? So instead of acres, can we talk in hydroponics and tiles level?
We have not tried it in that form, so we have tried it on photobioreactors because all the products that we needed to make.
See, I was thinking about he was interested in water and water flow. No? Whether this same thing can be used in canal waters instead of having a separate water flow for culture development.
Okay.
Use the canal waters. Assume the canal water level is regulated, and the solar panels are just skin deep at the canal.
Yes. I think they have done it in Gujarat.
Gujarat canal, they have covered it.
Yes.
The canal, and what I'm telling you, the algae culture needs water flow, means that the panel has to be underwater. Is it like that?
If that water is to be used for drinking purposes, then it is not wise to get these bugs mixed in that flowing water. For two reasons. One, these bugs produce sugar. So even if by themselves they are not pathogenic, the fact that they make sugars enables other bacteria in the air to grow, and they may be pathogenic.
That is generally irrigation canals, no? Is it irrigation?
So I'm coming to second point. Second point is algae are known to soak up a lot of phosphorus. So whatever phosphorus is there in the water will be taken up by these algae. And thirdly, some of them, I don't think any of these species are bloom. They cause algal blooms, but the algal blooms at times. I'm most interested in listening to what and how Natarajan sir solved this problem.
Unfortunate that he stuck with some communication. And another thing, he had a recent issue, so he's not very strong.
Okay.
He had a recent some heart surgery or something.
Is it possible to see the PPT, sir, if it's allowed? I mean, if it's.
Yeah. Any of the slides are there, Rajeshji?
But I said it's okay. Go ahead.
Go ahead. No, what is there? We have another scientist here.
Oh, what's that? Okay, so they are talking about using microalgae to make fatty acid methyl esters and biodiesel. So many of these bugs are known as oleaginous algae or oleaginous cyanobacteria. They are known to produce and store fatty acids inside their cells. So they tend to grow fat. I mean, if you look at a microscope, they appear very fat. They are fat because there is a large oil droplet inside every cell. So the other cell organisms are just crushed in a corner, while the oil droplet occupies most of the space, almost 90% of the space available inside the cell.
So Amrish, I have a question. Supposing I have a huge pond where I can produce algae, and every 10 days I can take it out as a crop yield. So I can take the crop every 10 days, take the yield, the algae out, and I also have a large storage in which I keep storing this algae in, where it dries out. Okay. So will I be able to store that energy as long as that algae does not catch fire? That I have stored that energy in that form. Is that possible?
So it won't catch fire because it will have a lot of water content. So that is not an issue. Issue is it is ready-made food for other bacteria living. So other bacteria like fungus, etc., will grow on it and convert it back to CO2.
So how soon do I need to convert it into oil? And how long? What is the shelf life?
When we say we convert it into oil, what we do is we break open every cell, and that breaking open, it's called cell lysis in biology. After we lyse the cells, the oil droplet which was formed in every cell comes out and forms a layer that can be separated, and that oil is treated using chemicals to make this esters, ethyl or methyl esters of fatty acids.
So how long can I keep it without losing the oil back into CO2? How long can I keep it?
The moment you remove out of the water, and even while it is in the water, there will be some other species of microorganisms which will be growing and feasting on it. So moment
no cell life at all.
Yeah, moment you remove it, your timer begins. So the faster you do, the better yields you will get.
And what is the process of converting that into? Is it a costly process, or is it something which can be done
from oil to diesel?
No, from algae to oil. Because once you convert it into oil, it is stable, I suppose. Then it will not.
Yes.
So algae to oil, how long does it? What is the process?
That is the most critical bottleneck. Not just for algae, but there are various fungi. It can also make oil. We call them oleaginous fungi. The breaking open of every cell.
No. There is one more thing, that even if there is a cost.
Yes.
See, it's a strategic investment and has some geopolitical implications.
Agree.
That cost may not be a matter, the strategies may be a matter.
Agree.
So, commercial grade ISO, suppose JanyuTech takes up. Can we immediately see a light in a year or two the commercial levels?
Sir, if I'm not mistaken, Reliance is working very hard on this exact problem, or this exact year. While I was doing, I was in IIT Bombay. 3 or 4 PhD students were working in collaboration with Reliance Life Sciences on this exact problem, producing algae, using algae to make fatty acids. So they have achieved a good.
So Amrish, So the issue. My question is,
what I just let me finish one line, sir.
Yeah.
I don't know the exact value in rupees, how much it takes to convert from 1 kg of dry cell mass of algae to 1 kilogram of oil. But what I know is, among the oil-related operations, that is one of the significant chunks where money is, it requires higher amount of money. And that has become a rate-limiting step in many of such projects.
No. The point is this, that even at the cost of today, our petroleum import bill is more than $300 billion.
Agree.
So, if you want to reduce your dependence, and they keep saying that we must be producing things locally, and even if it is at a cost. So if the government is ready to bear that cost of conversion, and you have ample sunlight. The only thing which you have abundant in this country is sunlight. So if you can produce, local production, you can reduce your dependence on West Asia from Middle East and Russia on energy.
In principle, yes.
The government may be ready to fund that balance amount.
In principle, yes, but in practice, थोड़ा problem है इसमें. Again, I will talking more from microbiology point of view. The rate of growth of this algae is considerably slow. Algae, since they are in the simplest words, algae are miniature plants. So they convert CO2 into all sorts of organic chemicals at much faster rate than, let's say, a plant can. So the turnover rate of microalgae for producing almost anything, oil or other, if there are any other molecules of our interest, is when we compare it to plants, is very high. So again, producing. So the biodiesel per se is typically a fatty acid molecule of C10 to C16, C18. Typically, we call it medium chain fatty acids. So anything more than 20 usually is not there. Out of these C10, 12, 14, 16, 18, C16 and C18 long fatty acids are the most predominantly available fatty acids that are produced by almost every life form. What happens in biodiesel is, and since it has 18 carbons or 16 carbons, the calorific value of that is equivalent or almost similar to what we get in petrol or diesel, because even the diesel and petrol molecule has almost equivalent number of carbons. So it is when we say about calorific value, it's about how much energy it contains per, in very simple words, per kilo. So energy density. That's what we're talking about here. So since molecules that are called as biodiesel have almost comparable number of carbons as in petrol or diesel, so the energy output from such molecules is also comparable. So they are very easily usable in standard internal combustion engines as compared to, let's say, ethanol. So ethanol, while it is very easy to make, and we are putting 10% of, whatever petrol we buy nowadays, almost in every petrol pump, 10% of it is ethanol. But ethanol, the problem is that ethanol had only 2 carbons. So the calorific, although it can be easily blended in petrol or gasoline, the energy output of ethanol is not equivalent to petrol. So whenever it is running on a blended petrol, that is ethanol, the energy that is power output of that engine is relatively lower. And as compared to the diesel engine running on biodiesel, or either full-fledged biodiesel or blends, whatever. So we don't have that.
Can you take it that the petrol what you are getting after ethanol mixing is an inferior petrol than a regular one?
I didn't get you. I didn't understand you.
नहीं, ethanol mixing के बाद जो मिल रहा है petrol, this is an inferior calorific value or inferior material than what we are getting outside.
Calorific value wise, yes, but it doesn't. It is good for various other engine parameters, and also it helps in improving our energy bill as a country. So there is.
I think this is the schematic of what set up the BOT.
Okay. Yes. This is a. It's a lagoon. So basically water flows in various loops here to increase the amount of time flowing water spends inside in presence of light. So this zigzag path that has been given to water is to A, increase the surface area, and B, reduce the residence time, so that the algal cells can stay in presence of light for longer duration of time in given area.
It is like solar water heater.
Sir, basically it's about how long can algae, do you give your algae or bacteria to stay in presence of light. The longer they stay, the longer will photosynthesis run, and longer photosynthesis runs, more molecules of our interest they will produce. So by giving this path, and most of them are very shallow beds. So as the algal blooms get thick, the light penetration starts becoming an issue. So you can't really have a very deep ponds. At least that's what the problem is faced in photobioreactors. The photobioreactor design is very different from a normal bioreactor, which is usually cylindrical. Photobioreactor is usually rectangular or cuboid with a very rectangular, that's a word. So that light can traverse through entire cross section, and all cells in that cross section have equal or almost equal access to the light. If we increase the thickness and after algal bloom becomes very thick, so बहुत high cell density growth आ गया है उसमें, so the light simply won't penetrate and there will be a dark zone after a few inches, or depending upon how thick the algal bloom is, of course. So that becomes a constraint. So A, they have to be really well mixed, and B, longer time they stay in presence of light. While being well mixed, the chances of almost all cells having access to sunlight improves, and the depth of this pond should be not very deep. It should be relatively shallow, so that intense sunlight, let's say summer May ka mahina mein, at least for 7-8 hours a day, all the pond will be lit through and through, so that more algae will have access to light and they will be more efficient.
One more thing, Sabreji.
Yes.
We are talking about the algae growth, right?
Yes.
You are talking about fungus also, right?
Yes.
So which one has got a better this thing, and which is commercially closer to coming to commercial?
You're talking about algae. I mean, for production of what? That's my question.
Production of this oil.
Yes. So, sir, actually for hydrocarbon oils, none of them are commercially viable. Simply because when you choose algae as the platform organism, it has its own pros and cons. Pros being, you don't need to add any sugar source. You don't need to add glucose, etc. for it to grow. It grows by fixing carbon dioxide in the air, and does all the chemical reactions on its own in presence of sunlight. So it's very cheap in terms of operations, but it's also very slow growing. So you have to keep the plant on and open for longer duration of time. Hence, the competing organisms which are known to grow on these bugs, they tend to overgrow. So there has to be certain methods, certain chemicals, certain things added, so that the unwanted bugs don't outgrow our fungi. And our fungi are the only dominant species left inside the pond or fermenter or whatever of our interest. So this is the con of using algae or cyanobacteria as a platform. If we use fungi as a platform to make diesel or oil, the biggest pro is they're very fast growing. So you can have let's assume you choose yeast, or you choose some oleaginous yeast. So the doubling time of every yeast is 120 minutes, 90 minutes. So you can have batches starting and ending in 24 hours to 36 hours. You can actually build large tanks. There is no inhibition of itna depth chahiye, etc. You can really build 1 million liter tank, cylindrical tank with impellers, etc. and provide sugar. So usually, if the chemicals that you are making are of high value, then people go for fungi than algae. But if the chemical of your choice is of low cost but high volume, like fuel, for example, then algae becomes an interesting option.
Natarajan's view is that to make algae grow faster, we use the existing infrastructure. See, his additional point is that it is not that we are creating a separate infrastructure for its growth. Existing solar things can be used.
Yes. That I don't get. That's what I was interested in. But because I'm talking about how we traditionally do it in labs and pilot scales.
Okay.
So in pilot scales and labs, there are photobioreactors. So I'm talking from that position. With something new being tried here that I don't know, and I'm most interested in knowing how it.
We'll get the details from Mr. Natarajan, right? And we'll work on that in a detailed way. Because see, existing infrastructure giving additional output. in addition to Bijli in the daytime. If the same setup is going to give with a small amendment, then actually it will become much viable.
True. There's one more interesting point here is also choice of algae. Which species will you use? So for example, I had published a paper when I was in IIT Bombay, where we found very fast. When I say very fast growing, it's relative. I think it's as fast growing as bacteria. But in compared to its peers, we found a very fast growing cyanobacteria. So it's also about what choice of bugs. I mean, again, I'm talking from microbiology point of view, not engineering point of view. Which choice of algae, which species of algae you choose. So some algae might be very good at accumulating more oils per unit time, but they are more fussy about some nutrient. अगर वो हो गया या if presence or absence of some chemical is deal breaker for them. On other hand, there is a robust fungi or algae which can make half of the oil, but can. I think
what I was keen also, if someone can note down the discussion issues are Ajay, someone can note down the points while we are discussing. See, we are seeing power plants on the surface of sea.
Yes.
Solar installations.
Yes.
Right. And solar installations are literally water is just flowed by the atmosphere is almost 90-93 RH.
Yes.
So whether that RH is sufficient enough for the algae to grow, or we have to really submerge it under.
No, these algae are water based. I mean, they are growing in water. So relative humidity is of not that consequence for algal growth.
Whether that is sufficient or it has to be underwater.
No, they have. Even if you put it underwater, they'll swim upstairs, sir. They will try to be and compete with each other to get more and more sun.
Amrish, is it possible to grow algae in salt water, sea water?
Yes. When every day, when I was doing again our postdoctoral times.
Okay. If algae can grow on moisture, then all these solar panels which are on the sea surface can be use more than the power, because transmitting power from the sea towards the land again.
That I couldn't understand. I mean, are we talking about using solar panel, solar cell as a surface on which algae will form a biofilm? I'm asking, because if that is the purpose, then the solar cell won't function as solar cell. If the biofilm becomes that thick.
They are doing the flow.
I don't know. I don't know how the scheme of things.
And sends out excess photons. We expect solar PV to use these photons also to produce power. We work with Tata Power to develop and fabricate this solar PV system. Slope is provided 2 to 3 degrees slope for the water to flow. The width of the solar PV is 1.5 meters and length is 100 meters. And we have to provide this is what is all the structure or architecture of the system what they have developed. At the end of the raceway, the matured algae containing around 30% of oil is filtered. The oil will be extracted, used for biodiesel production. The cake can be used for anaerobic.
It's a very interesting observation. Considering the acre and the output, it's a very interesting thing.
Abhimanyu, Dr. Natarajan has heard all our questions and doubts, and he is very happy with the presentation that we have generated out of his emails. And he says that I would like you all to put down all the questions that you have, doubts you have. I will answer all the questions. I'll send you each of these answers or by mail. Thank you. Thanks a lot. Thanks everybody.